Hello everyone. So in the last video, we've seen another example on how to use, how to find out the variables if you have certain points in a given shape. We've already looked at the parabola. We've always seen straight lines and how to solve those equations, like in linear equations. And then we went and checked out parabolas, and then we dived into circular shapes. So the bottom line was, the conclusion was that whatever it is the shape that you're working with, as long as you have certain points on that shape, you can easily calculate the different variables you need from the equation of that shape by substitution. Of course, you have elimination and you have other methods as well, but generally speaking, what we're saying now is that there's an easier way to solve equations regardless of the number of the variables you have, which is through matrix and matrices. So matrices are really good alternative to solving those problems, and then we can dive into them right now and see what do they talk about. So following on the series that we've been following so far, an introduction to matrices.
Why you? In the last several lectures, we studied systems of two linear equations in two variables, and systems of three linear equations in three variables.
Either way, in either of the systems, we already know how to actually solve these equations. We have elimination and substitution, and if it's two equations, we can opt for either, and if we have three equations, we can also opt for either, but it's best to take two equations and solve them, do the elimination on two of them, get a new function, and then do the same for the other two. And then you just substitute each and every one on the other one, whatever.
And we have seen how these systems can be solved using the methods of substitution or elimination. Although these methods can be used for systems with any number of variables or equations, as the number of variables and equations increases, the systems become much more difficult to solve. Because of this, mathematicians have devised methods of solving systems of linear equations using matrices, along with a series of operations which can be performed on these matrices to solve a system, regardless of the number of equations and variables. In this lecture, we will introduce matrices and see how they can be used to represent systems of linear equations in a compact, easy-to-manipulate form.
Nice.
A matrix is a type of mathematical object, just as numbers, variables, and expressions are types of mathematical objects. A matrix is a rectangular array containing individual elements or entries enclosed in brackets. The entries of a matrix
We can have this recorded.
Objects.
So they are a type of mathematical object, just like a function, like in a function. Anyway, so each element is called an entry. There we are.
A matrix is a rectangular array containing individual elements or entries enclosed in brackets. The entries of a matrix can be numbers, symbols, expressions, or any type of mathematical object for which the operations of addition and multiplication have been defined.
Now, the matrix. We have functions.
This requirement is necessary since some matrix operations involve addition or multiplication of individual entries. The entries of a matrix are arranged in rows and columns.
So each element is an entry.
And a matrix can have any number of rows and any number of columns. A matrix of m rows and n columns is said to be an m by n matrix.
Equals x n. Right? Is that it? Or maybe n like this. M x n. Start multiplication again. X n matrix size. No, I didn't know that was the if it's double. Matrix size. So the matrix size is m minus n. M indicating rows and n indicating columns. Well, this lesson of matrix is actually the long-awaited lesson that we've been waiting for. All of this efforts, or all of these previous lessons are an effort for this exact moment. So let's see.
For example, this matrix is a 4 by 5 matrix. So we say that the dimension or the order of this matrix is 4 by 5.
This is matrix order. Matrix order of size is m by n, just like what we've seen in the previous videos of sets.
Order of a matrix is always given as the number of rows followed by the number of columns. The rows of a matrix are numbered from top to bottom starting with row 1. And the columns are numbered from left to right starting with column 1.
This is important to have. You could have this here. It's the bottom and left, right.
The position of an entry in a matrix can be specified by its row and column numbers. These are called the indices of the entry and are written as subscripts following a variable which represents the entries in the matrix. For example, if we choose the variable a to represent an entry and I and j as the subscripts, we can refer to the entries by writing a, where the first subscript I is the row index, and the second subscript j is the column index of a given entry.
We could use this better than the other one. And each element is indicated by its row and column.
For For example, we can specify the entry in the third row and second column of this matrix as A with subscripts 3, 2. In this array, the value of that matrix entry is 1. The main diagonal of a matrix is composed of all the entries whose row and column numbers are the same.
So let's do the diagonal. Elements element of the same row and column number for the same diagonal. I think these important terminologies would make things a lot.
One special type of matrix is a square matrix. Square matrices have an equal number of rows and columns. If the number of rows and columns in a square matrix is n, we say that the square matrix is of order n. For example, this square matrix is of order 4. An upper triangular matrix is a square matrix whose entries below the main diagonal are all 0.
Now, there are a lot of terminologies here. Oh, never. The numbers below the main diagonal, below the main diagonal, and they're all zeros, is called upper. What is it called? Upper what? Upper triangular matrix. Upper triangular matrix. So it's always easy to get a picture of it. I've already done so, so I'm just gonna paste it here. Next, I'm guessing we'll be seeing a lot of others.
The entries in the main diagonal and above can have any value, 0 or otherwise.
Because what I think of is that I think we should take this look, this take snapshot better than the other one since it describes the red cloud. But I think there is also another type of matrix, if I'm not mistaken, which is all zeros. Let's see.
Likewise, a lower triangular matrix is a square matrix where all the entries above the main diagonal are 0.
Well, in this case, things change a bit. When it's inversed, when it is inversed, or the inverse, it is lower triangular matrix. So
In a lower triangular matrix, the entries in the main diagonal and below can have any value. A diagonal matrix is a square matrix whose entries above and below the main diagonal are 0.
see, now this is a different story. They're not all zeros. Diagonal matrix. When both entries above and below the main diagonal call the matrix main, what do you call it? Main diagonal matrix. Matrix. Nice stuff, eh? What else do we have?
Other special types of matrices are matrices with only a single column, called column matrices, and matrices with a single row called row matrices. Another special type of matrix, which is useful for solving systems of linear equations, is an augmented matrix.
Interesting. This is what we really dive for, right?
As we mentioned in the beginning of this lecture, augmented matrices are used to represent systems of linear compact, easy to manipulate forms to represent systems of linear equations in a compact, easy to manipulate form. Augmented matrices are like other matrices with the addition of a vertical line and an additional column of entries to the right of that line. Each row of the augmented matrix is a shorthand representation of one equation of the system.
So each row is a representation of a a corresponding equation or an equation. I'm not sure if it has to be. Yeah, it has to be.
System of the augmented matrix is a shorthand representation of one equation of the system, each equation.
X coefficients, Y coefficients, and the rows. The rows are the coefficients of the equation.
Any variable without a coefficient is considered to have an implied coefficient of 1.
Coefficients. So that's basically 1, yeah. That's
And any variable in the system which is missing from an equation
0. So we could for any missing variable, you get a 0.
The entries in the column to the right of the vertical line correspond to the constants on the right side of each equation, corresponding to the equal signs in the equations. Now let's look at a few examples of systems of linear equations and see how to create their augmented matrix representations.
I think the rest is going to be like straightforward.
When creating an augmented matrix for a system of equations, remember to first make sure that the equations are in standard form, with the variable terms on the left side of the equal sign and the constant terms on the right.
Side.
The variable terms should appear with the variables in alphabetical order, going from left to right. And remember that any variables without coefficients have an implied coefficient of 1. From an equation has an implied coefficient 3 variables contained any equations with less than 3 variables, then the equations might appear like this.
Yeah, but you have to match.
Before creating the augmented matrix, you may find it helpful to create a table of variable coefficients. Placing the coefficients for each variable, including any missing variables, in the proper rows and columns of the table. So let's start by creating an augmented matrix for a system of 2 linear equations in 2 variables. To create the augmented matrix for this system, we first collect all the coefficients and constants for each equation. Since in the second equation x has no coefficient, its implied coefficient is 1. We then collect the coefficients and constants for each equation and enclose them in brackets with a vertical line separating the coefficients from the constants. To create an augmented matrix for this system of 2 linear equations in 3 variables, we start by filling in the implied coefficient of 1 for the x term in the second equation. We then collect the coefficients and constants and enclose them in brackets with a vertical line separating the coefficients from the constants. To create an augmented matrix for this system of 3 linear equations and 3 variables, we must fill in the implied coefficients of 1 for the terms with no coefficients, and the implied coefficient of 0 for the missing z term in the third equation. We can then collect the coefficients and constants and enclose them in brackets with a vertical line. Likewise, to create an augmented matrix for this system of 4 linear equations and 4 variables, we fill in the coefficients of 1 and any missing terms, collect the coefficients and constants, and enclose them in brackets with a vertical line. As a final example, we will create an augmented matrix for this system of 5 linear equations in 4 variables. We once again fill in the coefficients of 1 and the missing terms, collect coefficients and constants, and create the augmented matrix. So far, we have seen how to represent systems of linear equations using augmented matrices. In the next lecture, we will introduce 3 matrix operations called elementary row operations, which are used to transform an augmented matrix to a matrix representing an equivalent system of simpler equations, which indicate the solution set of the system.
That is exactly what we're looking for. So I'm going to leave that to the next video and follow up on that. The next video is probably going to be a silent one, which would mostly be probably be us listening to the videos. I know that I sometimes get some background noise, background interruptions. But yeah, until the next video, have a good